back into this. We've got our foundational knowledge down, so we are all on the same page. We should be able to move through this next section um, pretty easily. So we're going to kick it all off with the Big Bang Theory. So everybody pretty much knows what the Big Bang Theory is. It's how the universe was formed. But that's the common mistake. Big Bang Theory doesn't really tell us exactly how the universe was formed. We don't know. We don't know what there was before it happened. We don't know how it happened. We don't know if it was a bang. We don't know what started it. We don't know anything. Um, but this is the kickoff. We know that our universe is expanding, and this is where that expansion started. That's pretty much the extent of it. We actually can't trace back to the very, 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 very beginning of time. We get to about 10 to the negative 43rd seconds into time. Ridiculously small amount of time. It's just like this little teeny window that your brain can't even comprehend between nothingness and our universe. And that's pretty cool. So that little sliver of time that we just can't figure out, that is the Planck Epoch. That is what we're talking about. That 10 to the negative 43rd second, that is where it all started. We don't know anything about it. We have theories, and I'm not even sure that you would call them theories because we don't have any way of proving their plausibility. We have ideas, mostly is what we have. And there's some good ideas out there. There's some ideas that kind of fit the structure of what we would expect to see, but we have no way of testing that because the Big Bang's already happened. So, when we talk about the Big Bang Theory, because there's that little speck of time in there that we don't know exactly what happened, but we know it was a lot, and it was extremely significant, we have a term that we call meaningful time. So everything before 10 to the negative 43rd second is before meaningful time, including the Big Bang. We don't even know if there was time. That is really interesting as well. We know that time is part of the fabric of space. We know that. That was proven by Einstein's theories and many, 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 many other theoretical physicists. So we know that in order to have time, we have to have space. And if the Big Bang was the beginning of our universe, that means it was the beginning of space. And if it was the beginning of space, it had to be the beginning of time. So it's hard to kind of comprehend that and put your brain into that mindset that there was some, and you even want to say point in time. There was some point in time, but it's not time. Time didn't exist. We have no idea what existed. None. Because we know that the universe is expanding, we theorize that it had to have been extremely small, just this little pinprick of existence, completely packed, full and dense, just as dense as it could be. It would have been extremely hot, and something in that little speck set off everything. Everything that we have here on this planet, everything that we have out in space, everything we know, everything we don't know would have come from that little speck, what we assume is a speck. So the reason that we assume that it was condensed and it was a speck was because of a scientist named Hubble, like the Hubble telescope. So Hubble studied light waves. And everybody knows what the rainbow looks like. That rainbow is representative of different rays of light. Light travels at different frequencies, just like sound does. Blue light waves are short, red light waves are long. And just like sound, just like when you're talking or listening through speakers, the further that sound wave travels, the more spread out it becomes. Light's exactly the same way. So when you study light coming from a particular point, if you see that light becoming, they call it a redshift, it starts moving through and the waves start getting more spread out. It's called a redshift. Um, that that indicates that whatever you're looking at that's giving off that light is moving away from you. The opposite of that, like I said, blue waves are short. So if you are studying something and you see those light waves getting shorter, we call it a blue shift, and that means it's moving towards you. So that's how we found out that the universe is expanding. Um, we didn't know at that time how fast, how slow. We just knew that the things that we were looking at were red shifting. They were getting further away. And that was significant. And that's significant for a lot of reasons. One of the coolest reasons is when we start talking about dark energy. It's really, really cool. Um, so now that we know that our universe is expanding, let's take a look here. The next major thing that we discovered was dark matter. So dark matter is really interesting. Um, we don't know what it is. It's kind of like that Planck Epoch. We don't know what happened during the Planck Epoch. We don't know a whole lot about dark matter yet. Um, we know that it's there. We know that it's there because we can observe its effects on things that we can see. We can't see it. We have no idea what it's made of. We have theories. Theories are great. They're so fun. But sometimes it takes lifetimes to prove them or disprove them. But it's interesting, the stuff that they discover while trying to prove these theories or disprove these theories. It's really, really cool stuff. So dark matter, we discovered it in the 30s. So it's relatively new in the field of astronomy and astrophysics. We discovered it in the 30s. The reason that we discovered it was because scientists were observing objects in space, and they were observing their orbits, they were observing their velocities, they were observing their masses. So they would calculate the mass of an object. They would take everything that we know about gravity and other forces, and they would apply it to that object in consideration of its mass and try to map out its velocity in orbit. Now, they noticed that when they did this, they were not coming up with the numbers that matched what these objects were actually doing. So the objects were moving at different speeds or in different directions. They were not orbiting the way that scientists predicted. And scientists were very meticulous about how they predicted these orbits. So they knew that if these objects weren't orbiting the way that they thought that they should be orbiting, there was only one of three reasons. They either calculated the mass incorrectly, there was stuff that we didn't know or had wrong when it came to gravity, or there's something there that we don't know about. We can't see it. We have no idea it exists, but it's having an effect. It's having either a gravitational pull, which means it's got to have mass. There's an effect going on there. We can see it. So the easiest way to rule things out is to start with what you can see and what you do know. So they went back, they double checked their work. The masses that they had calculated were right. A lot of studying on gravity going on in this time frame, and they find out that their studies on gravity were correct. We were not mistaken about gravity, so that left us with there's something there that we don't know. So this became known as dark matter. And it's really difficult to study something that you can't see and that you know nothing about. So studying dark matter has been really interesting. We don't directly observe dark matter. We observe the things that we see that are being affected by dark matter. So when we see something curious that we're not expecting out in the universe, we go through, we double check all the stuff that we know, that we can prove, all that stuff. If we still can't explain it, it kind of gets chalked up to dark matter, which it's fair, you know. Dark matter just means that there's something there that we don't know enough about to be able to appropriately label it. But at the same time, I mean, we could be attributing things to one specific type of thing, and it could be 4 or 5 different types of matter out there that we don't know, don't see. So we just aren't completely certain. We just call it dark matter as though it were one type of thing, and we attribute all these unexplainable effects to it. Um, but we're studying. We're trying to figure out what it is. I mean, there's neutrinos. And this is all stuff that we'll get into later down the road because it gets kind of complicated. I want to make sure that we break it down so that you're not overwhelmed when we get there. But there still to this day, we discovered it in the 30s. We're still trying to figure out what it is. The Large Hadron Collider, that is part of our studies on dark matter. That's where we're trying to break things down to, even smaller particles than subatomic particles. We're trying to get it down to the smallest possible thing that it could possibly be and equate those effects to what we've seen in space and chalked up to dark matter. It may not happen in our lifetime. It may not happen in many lifetimes, but we're setting the groundwork. We're setting the pace. We are going back and reevaluating what we know. So, we're building a foundation to eventually figure it out. It's still a mystery, though. So, in addition to dark matter, there is my favorite thing. I really like this. In addition to dark matter, there's dark energy. Dark energy is really, really cool. So, in 1998, I believe. I'll have to double check that, and I'll put those in the notes on the archive. 1998, scientists set out to determine what rate was the universe expanding. What they expected was the Big Bang happened, bam, everything got shot out, and gravity and other forces acted on everything that was shot out from the Big Bang. And yes, our universe is expanding, but it's slowed down a lot because it was forceful during the Big Bang at the blast. And as we move away from that blast through time, the expansion should slow down. So based on everything that we know, that made sense. So these scientists set out to kind of prove that hypothesis, and they did it in a really interesting way. So there's a type of star called a white dwarf. We'll go through all the different types of stars and their characteristics at it during a lesson on its own. These are worth going over on their own. There's something special about these white dwarfs, though. These white dwarfs like to pair up with other stars. When they pair up with another star, we call it a binary. And these two stars, their masses act on each other. And there's gravity in space. Most people think there isn't, but there is. It's not as pronounced as what we feel here, but it's there. So when they pair up in these binaries, they begin to orbit each other. And when they begin to orbit each other, this white dwarf star becomes a bit of a leech, and it starts pulling mass from whatever star it's orbiting with. And they can pair up with any kind of star. They can pair up with other white dwarfs. They can pair up with any kind of star that's out there to create this binary. But once the binary is created, they start to leech off of that other star, like a parasite, kind of. And the interesting thing about white dwarfs is they are kind of regulated by their mass. So instead of having to reach a critical heat, instead of having to reach, this specific variable for any of its characteristics to supernova, white dwarfs always supernova when they reach a specific size. I say always. There's very, 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 very rare exceptions. So most of the time, though, they reach a certain size, which is only slightly bigger than our sun, and then they supernova. There's an interesting effect that this causes. Since they go supernova at the same exact size, they tend to release the same amount of energy. Light is an energy, so they are the same brightness when they supernova. It's just uniform across the board. You can expect them all to be this bright. That's really awesome because it meant that since they are that uniform across the board, Scientists could look for these A1 supernovas, that's what they call them. Um, they could look for these A1 supernovas out in space. When they found one, they would identify the universe that it was in and make all their notes. And then after a certain amount of time had passed, they would come back, they would find that universe and that supernova again, and they would measure it again. So now we know that the supernova's gone from here to here, and we know how fast it happened. Because we have a distance, and we know how long it took in between those measurements. So we have time, so we can calculate speed, right? So, pardon me. Speed equals distance over time. With these two measurements, we had distance and we had time. When they calculated this out, they were extremely surprised because everything that we know tells us that the universe should be expanding at a slower rate, but the universe is accelerating. We're getting faster. That means there's got to be something there causing the acceleration. So we've already accounted for every type of energy that we have discovered, that we know, that we've studied. Pardon me. And it's none of those energies. This means it's one that we don't know. And just like dark matter, we can't see it. We're not able to directly observe it. So again, just like dark matter, we observe its effects. We take everything that we know and we apply it to these things that we see happening in space. And we look for anomalies that we can't explain. We find those anomalies, we single them out, we study them, we just try to come up with an explanation. And when we fail, we know that we need to chalk it up to either dark matter or dark energy. They're both still very, very, very theoretical. But the reason that they are important to discussing this lesson here is because there are some circles of thought that believe that in that tiny pinprick, right at the very beginning of time, that may have been the first place that dark matter and dark energy showed up. They could have been the catalysts for the Big Bang, which is really cool. And the thing that I really think is rather kind of mind-blowing is scientists have been able to estimate how much of the universe is comprised of dark matter and how much is comprised of dark energy. And dark matter accounts for about 27% of the universe, and dark energy accounts for, I want to say it's about 68%. I'll have to double check that. Anyway, so total, if you talk to astronomers and astrophysicists, they will all kind of be on the same page and tell you we only know and can identify about 5% of the universe. 5%. That's it. 5%. Every single thing that you see on this planet, nothing. We can only account for 5% of the universe, and we're still trying to figure the rest out. That's pretty incredible. So that's what I got for you guys today. If you guys have any questions, feel free to leave them in the comments when the archive is posted on the channel. And I will definitely keep any subscribers up to date here and on Facebook. You can find us on Facebook at Rebel Rebel. I will put that link down in the descriptions as well. Any questions, please don't hesitate to reach back out to us. Any suggestions, feedback, we love it all. So don't hold back, guys. I hope you guys enjoyed this. It was a lot of fun to discuss it with you guys. And thanks for joining us. Bye-bye.